Okay, for our next question, we want to figure out how to state work as an integral. And so the answer given here is the calculus 1 method. I'm going to show you how to derive this fact. And in calculus theory, you're not going to assume that f of x is equal to kx in any form or manner. We're just going to take f of x as f of x. And so we know that the really simple version of this question at the high school level can be stated as this. So we know that if we have this 2D question, the work done by a force imparted at this angle to move object M through a distance vector D is going to be the dot product of the two. And this is going to be the magnitude of F multiplied by the magnitude of D, cos theta. And this is in the scenario that F is constant. But we know that this is not always the truth. A very good example of this is rockets trying to reach escape velocity. The force that we would be dealing with is the gravitational force, and that of course is dependent on your distance from the surface of the Earth, and that is changing as the rocket is trying to reach escape velocity, which means that the force will not be constant. So how we state it as an integral is we're going to take account of the fact that f is changing, and we're going to integrate f as it changes along its path. And so a good way to imagine this is take an object moving along path C, and for this very short part of this path, it moves dl, and the vector tangent to it is going to be t, and it is moving in a vector field f. So it is moving along path C that is parametrized or described by R of t, and moving through this vector field of f that is also going to be dependent on R. In this case, the work done over this very small part is going to be what we've calculated. So the tangential force dotted with dl. So that's just going to be dl, not dotted with the force dot product with this distance, and that's going to be the tangential force multiplied by dl. And so let's write that out like that. And so we know that the force tangent is just the dot product of the force and the vector that is tangent. And lastly, we know that the tangent vector is going to be equal to the derivative of the vector describing the path over the magnitude of that derivative. Okay, and so now this will mean that when we want to find the work, it is going to be equal to the integral of dw, since it's a very small piece of the entire path. And that would mean the integral of ft dl, which would be the integral of f dot t, but we're going to write in t as this. So f dot r prime t over the magnitude of that dl. Okay, and then next up we need to remember the fact that dl is equal to the magnitude of the derivative of that vector dt. And so now let's put that in for our dl. We get the integral of the force dot the tangent vector, and then we're going to put in our dl. dt. These two will of course cancel out, and so this will give us the integral of f dot the derivative of the vector describing the path dt. And then lastly, you just need to remember that prime t is equal to dr over dt, which means that we can state dr is equal to this, which will simplify this to become the integral of f dot dr. And this will be our final answer. And so a really good example question for this is, as I mentioned, a rocket trying to escape Earth's gravitational pull. So we're going to use this equation that we've derived to find out how much work is done during that process as the force is changing. So as a quick sketch, we have this as our space. And so let's draw the Earth here. Okay, and we know that we're going to be trying to go from z is equal to RO, which is the surface of the Earth, to a point where the rocket has reached escape velocity, and it is at z is equal to RO plus h. Okay, and then later on what we're going to do is set the limit of this work function as h approaches infinity. So as the rocket gets infinitely far from the Earth, which is when you've escaped the gravitational pull completely, theoretically. And so we know that our path C, so first off, we know that the force that we will be facing here in terms of r is going to be negative g mm over r squared multiplied by r hat. Next up, we know that you're traveling, so the path is going to be along C, and C is a straight line that is along the z-axis. And so what we can do is set dr is equal to, z hat dz. And so along this path, x is equal to 0, y is equal to 0, r is going to be equal to z, and r hat is equal to z hat. And so now we just put that into this to get negative g m over z squared z hat. Okay, and so now we're just going to put all of that into the equation we found for the work done. So the work done is going to be equal to the integral of f dot dr is what we found. And so that is going to be the integral of negative g mm over z squared z hat. And then we know dr is going to be z hat dz. And so when we take the dot product of those two, it's going to be from z is equal to RO to z is equal to RO plus h, because we're finding how much work is done in between here and here. Okay, and so when we take the dot product and pull out any constants, we get negative g mm, the integral from RO to RO plus h of 1 over z squared dz. And for this, we can just easily use the integral of exponents in order to find out what that is. And so for a final answer, you will get g mm multiplied by 1 over z. And it's a bounded integral, so you want it from RO to RO plus h. And so when you actually do that out, you will get g mm multiplied by 1 over RO plus h minus 1 over RO would be the work done. as the velocity goes from the surface of the Earth to height h above the surface of the Earth, so RO plus h. And then remember, lastly, we want this to be escape velocity, which is when h is going to infinity. So we'll want the limit as h approaches infinity of w. And so this would be the limit as h approaches infinity of GMM 1 over RO plus h minus 1 over RO. And this is going to give us the answer of negative GMM over RO. And this would be the total work done as the rocket escapes Earth's gravitational pull. Since it's negative, that means that the gravitational field itself is gaining energy and work is done by the force to the field. And that's going to be our final answer. And so as your general equation for how to find the work done, we have it here. And you can use it for problems like the one I've done here.